Okay, let me talk about the applications piece. There's two things I need to talk about. One is about linear motion, and then one's about projectile, where gravity takes hold, and we have a different set of equations for it. So let's talk about linear. So linear, you just have to make sure that you describe the path of the object, or whatever it is, in terms of an x and a y, with that parameter of time. So this one talks about two tankers. So I need to have a parametric equation for tanker A and a parametric equation set of equations for B. All right, so it says they're leaving, and from one town to another it is 900 miles. So I know that between these two it's 900 miles. Tanker A travels at 18 miles per hour, so that's its rate times its time will be t. And tank B travels at 22 miles per hour. So when I go to set these up, I just put x and I put sub A for tanker A. So the x for tanker A is going to equal 18t, that's its rate times time. And this is just any arbitrary value you want to put. It's going to be going straight, it's linear, so I just said y would equal 1. And then xb, it was 22t, and y would be 1. Okay, now when you go to set up a window, sometimes you're going to have to do some solving to decide. I do know that the x's are 900 apart, so I know that can go from 0 to 900. And if I set my y's to be 1, I just want y to be from 0 to 2. So those I could set up. But for the time, I don't know how long it's going to take for both of my tankers to go from here to here. So you kind of have to do a little bit of math to figure that out. And I think I messed up here. I shouldn't have really said solve for D, because D I was thinking was like C, where it said how long does it take. But that wasn't really the question of D. So really what you have to do to find out when, you have to take the slower one, because you want to know, what should your time be. And if you want to see both of those ships, tankers going across, you want to make sure that you say, okay, for the slower one, it's good, which is the 18t is that distance, rate times time, has to equal 900. That's going to happen when t is 50. So I know my time should go to at least 50. So that's really what you needed to say here, is that that would go from 0 to 50. All right, how long does it take for the faster tanker, which is the one that's going 22 miles per hour? How long does it take to get to St. Petersburg? So 22t, when does that distance equal 900? That tells me I've gotten to St. Petersburg. So I just solve that equation. I get at 40.91 hours. Where is the slower tanker when the faster tanker reaches its destination? So in other words, when I'm at 40.91 hours, that's how long it took the first tanker to get to its destination. This says, where is the slower tank? So now that if I know in this answer my time was 40.91, I just have to plug that in. 18 times 40.91, that gives me, it was at 736.38 miles. That's how far it had traveled from the beginning. Okay, E says, when during the trip is the faster tanker exactly 82 miles in front of the slower tanker? So when I think of this, okay, here's my faster tanker, here's the slower one. I want to know, when is the faster tanker exactly 82? Well, that means if I took the distance the slower one has gone plus 82, so here's the distance the slower one went, plus 82, that should equal the distance that the tanker B went, the faster tanker. So when I set the distance the faster tanker went equaling to the distance of the slower one plus 82, I solved that and I got at 20.5 hours. And it just asked me when, it didn't say where, so that is my answer in time. And then F says, during what part of the trip were the tankers less than 60 miles apart? So if this is tanker B and this is tanker A, I want to know, when is that distance less than 60? So when I set it up, I just said, okay, if I took the distance of the faster one minus the distance of the slower one, when is that distance between them, because I subtracted, when is that distance between them less than 60? And so I solved that and I got less than 15. So really anything less than 15, which means from when they started to 15 hours, they were less than 60 miles apart. Now, if you want to see what that looked like on your calculator, I think I threw that on my calculator. Put it my y equals. I set my window to go from 0 to 50. My x's I set 0 to 900, and my y's 0 to 2. And if I graph that, now it's kind of hard to see. Notice you can't really tell that you can see the one starting to take over, but in here at the beginning it was hard to see. So what I decided to do is that instead of putting in my calculator what I had, I would go down, ignore the top ones here, these are on the bottom. I would look at that and say, well, instead of 1, maybe I would make the faster tanker be at, faster tanker or slower tanker, doesn't matter which one, to be instead of 1, make it 1.5. And then when you graph it, you can kind of see them side by side. And then you see the faster one starts to take off and get there sooner. Okay, so that's kind of how you can use your calculator to look at these two. And then you could look at windows in your tables as far as checking your answers to these. All right, so let's talk about the back side of the linear. I'll just show you kind of how I went through each of these to see if yours matched. This is Jack and Mark living 4 miles apart. Now Jack is traveling in this direction, and now Mark is traveling towards him. So when I set up my parametrics, I said, okay, the x value for Jack is 12t, and I just set an arbitrary y is 1. But now with Mark, because he's starting 4 miles over, and he's going in the opposite direction, like he's going towards Jack, I said he's going to start at 4, but now he's going to go minus 18 because he's going in that direction. So we have to make sure that we're taking the original 4 units away, but now as he walks, he's going to decrease in where he's at. So his position will go from 4 and it'll go towards 0. And again, that same arbitrary point, y value. So then when the question was, when and where will the boys meet? I want to know when the x's are going to be the same. So I set this x equal to that x. I set those two things equal, and I solved for t and got a fifth of an hour. And so then I put that back into here, 12 times a fifth, and 4 minus 8 times a fifth. They were both at 2.4, a position of 2.4, which means from the original where Jack was at, it was 2.4 units. That's where it was at. So Mark was, at the 2.4. It doesn't mean he went 2.4 miles. It meant it's 2.4 miles this way, which means it's really, what would that be, 1.6 miles from Mark. So when it says a position of 2.4, that means, okay, if you started at 0, that position is at 2.4. So at a fifth of an hour, they were 2.4 miles from Jack's house. That's what I had to say, because that position was from Jack's house. All right, the dog one, the only difference on this one is that the times were different. The dog took off, so there's his motion in a parametric. But then when the mom and Andrew took off, they were going 20 miles per hour, but their time was different. It was a half hour less than the time the dog was going. So now we have to adjust the times, because this is the time t. They were traveling a half hour less than the dog. And so then when I set those x values equal, I found out that happened at 5/8 of an hour, which is 37.5 minutes if you figure that out. And so that's the when. The where did they go? You have to plug 5/8 back in, and you get 2.5 miles away from their starting spot, their home. So at 4:37 seconds p.m., they were 2.5 miles apart. Okay, so that one had a little bit different twist to it with the time. Okay, and then this last one, it's linear, but it doesn't really follow that pattern we've had before. It's not horizontal or vertical. So with this one, you have to realize if they're at angles, we kind of go back to our vector stuff, and we say, all right, if I know I have a bearing of 40 degrees east, north 40 degrees east, I'm going this way. So my reference angle here is 50 degrees. That's my theta. And then if I was doing the other one, north 52 degrees west, my theta would be 142. And there's my R value. So when I set these up, it's x is the x component, which is 600 cosine 50t, and y is 600 sine 50t. For the second one, with this theta and r, it's 550 cosine 142t, but remember it's 1,000 to the right. So plus 1,000, I had to add that to the x. And then this is just my 450 sine. All right, so I set those up. That again, that has to do with the vector piece. Again, you have to figure out what is theta, what's the reference angle, and then the magnitude. And with the x's, the second x value, I had to add the 1,000 to get over to there. Okay, is there any danger of collision? So what I did algebraically, again, you could throw this on your calculator to justify your answer, but you have to show me the graph and go through the table. And sometimes I think it's just easier to algebraically do it. I set my x's equal to each other and solved. I got 1.22 hours is when the x's will be the same. And then when I looked at the y's, when will the y's be the same? They're going to be the same when I subtract. So I just subtracted this on both sides, and I got 121t equals 0. So that's going to have when t is 0. So the only time that the y's will be the same when t is 0. And that's when the x's are the same. So will they ever at the same time be at the same place? No. And so that would be an algebraic justification that you just have to set the x's equal, see what time, at what time are the x's equal, and at what time are the y's equal. If they aren't the same time, then they will not intersect or will not crash. Okay, so that is the linear motion stuff.